Professor Y. Gurdadyan, to be editors of International Journal of Modern Physics. He has published a monograph, Paradigms of the Large-Scale Universe, in 1994, and among his edited volumes are Ergodic Concepts in Stellar Dynamics, 1994, Chaos and Astrophysics in 2000, Fermi Astrophysica, 2002, Low-Dimensional Physics and Gauge Principles in 2012. He has used astronomical methods in establishing the ultra-low absolute chronology of the second millennium of Near East civilizations in the monogram dating the fall of Babylon, published by the University of Ghent and the Oriental Institute of University of Chicago. I now request Professor Y. Gurdadyan to please present his paper.
Thank you for representing me. Of course, it's a great honor to be here and to have the possibility to address you. Especially, it's a special experience for me, a person used to speak in theoretical physics conferences, to participate in such an interdisciplinary meeting with so many distinguished speakers. I'll speak about the concept of chaos and order in the universe, about the Western viewpoint, about the Western methodology. I will use some concepts which are already used in various talks during the previous days, quantum theory, chaos, Planckian, etc. And of course, and I will provide, besides the reviewing the present situation and partly a bit about the historical involvement of the basic ideas, also I will give some, represent some novel results, so that can be material for future discussions in the context of the Eastern and Western viewpoints on these basic concepts. I will show, during my talk, I will show several formula, very few, but the main message can be clearly understood without going inside those formulas. Those can be, are mainly given for those with mathematical or physical background, just to illustrate the methodology. But it will not disturb the main message, as I said. So, let me start with this, with the concept which also has been mentioned during these days, about the problem of the free will. Again, in the context of the Western understanding. So it is traced, can be traced since Saint Augustine, as you can see, and then the next discussion in the context of the Christian theology was the essential push was given by Thomas Aquinas, and then the next came by Erasmus, who discussed in details the problem as it was understood at that time, and arguing for the freedom of the will, arguing for the free will. And then soon after, Martin Luther, came up with a twice thicker opus, book, where he contradicted Erasmus, claiming just the contrary, about the absence of the free will. So these discussions in the 20th century involved also physicists. Particularly here I mentioned the paper of Schrödinger in Nature. And also, let me mention that Einstein, in his private letter to a friend, did a strict statement concerning this, the free will. It is one of the rare strong statements done by Einstein in this context. And Dyson also relatively recently discussed this in the context of the evolution of the physics and our methodology of the understanding of the nature. Another debate included debate between French mathematician René Thom and Ilya Prigozhin, Nobel laureate in chemistry, which you can, as you can see, here mentioned in few words about whether deterministic determinism and indeterminism in the dynamical laws. So let me go very briefly in a few words about this, what happens in 19th century. 19th century was governed, we can say, with the Western mentality, was governed by so-called Laplacian determinism, namely the statement done by Laplace in early 19th century that if the initial conditions of all the particles are known in nature, and once we have the dynamical laws of the revolution, at that time, of course, it was understood the Newtonian dynamics, then we can predict the nature. We can be everything predicted. And this way of thinking survived up to the end of the 19th century, until Poincaré, proving a strict theorem, showed, several theorems, but came to the conclusion that absolutely contrary. If a system is perturbed, then it has to be chaotic. If it has to be chaotic, in that it cannot be deterministic. And this changed the mentality of the Laplacian determinism, and this mentality survived up to 1954. So again, the statement by Poincaré that perturbed systems are chaotic, and of course perturbations exist everywhere, particularly the planetary system. We have the planets rotating around the sun, moving around the sun, and they of course perturbed slightly, but still they perturb the motion of each of them. So then it has to be chaotic according to Laplace. And suddenly, in 1954, one of the foremost mathematicians of 20th century, Russian, Andrei Kolmogorov, came up with a theorem which was a kind of unexpected for the mathematical community. The statement of the theorem is written here, but in words, it means that if the system is perturbed, then in some conditions, the conditions are mentioned here, but they are not so crucial, stability survives. Namely, not every system will become chaotic. And the quite interesting aspect, maybe one of the unique in the history of Western science, happens here when the theorem was given without a proof. So Kolmogorov's paper was two-page paper in Doklady of Communications of the Russian Soviet at that time Academy of Sciences, two-page paper without a proof of the theorem. And still the community accepts this. And only 10 years after, one of his students, Vladimir Arnold, to whom I happen to know very well and work with him in Moscow, and Moser in Germany, independently proved this theorem. This theorem, as you can read below, changed the belief existing during 50 years since Poincaré, that chaos is a is the inevitable property of any perturbed system. Almost at in the same time, in 50s, early 50s, an interesting activity was started by Fermi in the United States, in Los Alamos. In Los Alamos, as you may know, was going on the Manhattan Project, the project when the atomic bomb has been created, as first atomic and then hydrogen, and Fermi was one of the essential participants in that project. And for that project, the first ever computer has been created in Los Alamos, and one of those computers, called Maniac, has been used in early 50s, suggested by Fermi, to check evolution of a particular system. Namely, there is a chain of oscillators which are bounded to each other, and the boundary conditions are fixed. You can see here the Hamiltonian and anyway, so the non-linear potential for the interaction of the oscillators. And the numerical simulations using this computer Maniac have been used for number of particles n, as it is written below, 16, 32, and 64. So relatively very few by the modern standards. And below you can see sitting is John von Neumann, Feynman, and Ulam, Stanislav Ulam, other participants of the Manhattan Project, and particularly Stanislav Ulam, mathematician. He later continued the analysis of this problem. Why? Because what they saw during this experiment was contradicting what they were expecting. They were expecting that once this system of the oscillators, so the chain of the oscillators are perturbed, then by time the perturbation will dissipate and will move to the higher modes, and the equipartition will take place. What they saw was absolutely contrary. They saw, as you can see here, that the modes, here it is written the capital T is the period of the non-perturbed oscillator. So within some periods, particularly here you can see 56 periods, the first mode is returning, namely the main energy which is in the first mode initially, after moving to the higher modes, returns again basically to the first mode. Here I have shown also to the right, you can see I put in a musical notes the modes corresponding to the do of the first octava with the first note, and then the second octava do to the second mode, etc. And then you can see the half of the piece is written here, and if somebody plays with piano, you can see that it is not it moves to a chaotic mixture of tones, but instead one single note after some period is becoming the dominating one. Just for the ears can be seen the absence of this kind of equipartition. And so this Fermi considered this as a little discovery, and it was exactly in the context of the Kolmogorov theorem. Namely, if you perturb system, so any system in the nature is more or less perturbed, then chaos is inevitable. So this example, Kolmogorov theorem, says no, it is not so. You can perturb something, and still you can be you can be stable. So let me, yes, here are summarizing. I am discussing this example because also as a unique case, also like the Algorithmic theorem, also this, how the discoveries sometimes are being made. Some experiment is being performed with the aim of confirmation something, and they get something completely different. Of course, it needs some time to understand. In this case, this problem called FTP, Fermi Pasta Ulam problem. So I said Ulam is the mathematician, Pasta was the engineer, and Fermi. So this problem since still is not fully understood since 55. And there are thousands of papers, there are monographs, there are conferences devoted to this Fermi Pasta-Ulam problem. But still, the problem is not understood fully. And here are mentioned also some issues confirming how remarkable this is. Therefore, I mention this again as a methodological interesting event happened in 20th century, and the photo over there is Metropolis, one of the fathers of the first computer created in Los Alamos at that time, which was used in this small discovery, small but still not understood till now, as I mentioned above. So this is connected to another interesting or basic, let's say, property of our nature. This is the issue of arrow of time. So physicists are distinguishing several arrows, thermodynamical, when the entropy of a closed system is increasing, and then cosmological, the universe where we live is expanding, psychological, so we remember the past but not the future, electromagnetic, it is the retarded interaction, quantum mechanical, namely during the experiment we change irreversibly the wave function. The mechanisms of each of them have been discussed a lot, and particularly about the cosmological, I can mention then in mid-80s, in 85, when Stephen Hawking introduced the quantum cosmology and the wave function of the universe. He used so-called mini-superspace Wheeler-DeWitt equation to calculate the behavior of the, he considered the link between cosmological arrow and thermodynamical, and he concluded that if the universe will expand and then stop and then contract at some time, as it was believed at that time, then, namely, the cosmological arrow, which is now showing the expansion, at that time will become changed, showing the contraction. In same way, the thermodynamical arrow will be changed. Namely, when today we mix two fluids and cannot separate them, in the contracting universe, they will be separated themselves. In a year, Don Page showed another solution when the cosmological and thermodynamical errors do not associate so closely, and Hawking agreed that his conclusion was wrong. And he sometimes quotes in his popular books that it is a unique case when a scientist is agreeing that he was mistaken. Usually they don't do, maybe. So, but the problem, of course, exists, and there are two global viewpoints on this. One is by Roger Penrose, that the role of the initial conditions is crucial in the appearance, emergence of the arrows. The second way of thinking is by Ilya Prigozhin, which stressed the role of the dynamics, not of the initial conditions. I will say that not all among these 5 mentioned arrows are now considered absolutely independent. They can be reduced to 2, namely thermodynamical and cosmological. I mean, the rest 3 can be reduced to these 2 arrows. So here I mention one conclusion proved on a theorem level, namely that in order to have the appearance, emergence of an arrow, then 2 conditions are necessary. One is the decorrelated special initial conditions, and the second is no memory dynamics. Is known also Markovian dynamics. So, and here I mention how it can be shown that the Hamiltonian, when we have a quantum system which is interacting with a bat, then also there is a term which is describing the interaction term between the bat and the system. Then one can show the conclusion I mentioned, namely the necessity of both initial conditions. Each of them is not enough for the emergence of the arrow. One can show that only some pre-arrow can emerge if the initial conditions are given. But to have the arrow, the real arrow, as we see it empirically, one needs both conditions. And here, connected with the cosmological aspect with this problem, I will mention that we know now that the major part of the universe is in the dark sector. Namely, it consists of the dark energy, which we don't understand by our current physics, because our current physics is gravitating. General relativity describes gravity, while with dark energy we deal with anti-gravity. And the second is the dark matter, which is a minor part, but still is bigger than the observed part of the universe. So, once we speak about the arrow of the observable part, the minor part which we observe by our experimental apparatus, by our satellites, by our telescopes, laboratories or so, they are the smaller part of the unobservable universe. If so, then the dark sector can take the role of the bat, so that they can, because of the unobservability, can provide the mechanism of the appearance of the arrow of time in the observed universe. So let me very briefly mention that after Kolmogorov, the theory of dynamical systems has a great breakthrough. A lot of techniques have been developed, introduced, particularly by Kolmogorov-Sinai entropy, which is now called as one of the basic tools. After Lyapunov, exponents were introduced by Lyapunov in late 19th century. These are now the basic tools for strict study of the chaotic systems. And of course, there are big schools, the school of Kolmogorov here, Arnold, Sinai, and also United States, Mail. And so this, the activity in 60s and 70s had essential influence for the strict study, rigorous study of the chaotic properties in the physical problems. Here, the classification of the systems has been reached, new particularly effects have been introduced, and of course, this enters the agenda of the experimentators and the theoretical physicists in an essential way. So another example how it enters was the so-called Henon-Hayley system, because the time when galaxies were become to be studied, were being studied by always increasing power of the telescopes, bigger telescopes, bigger aperture telescopes, and then in different wavelengths, we started to understand that how the dynamics of the stellar systems, galaxies, is developed in different types of the systems. Namely, we know that the stars are interacting by Newtonian gravity. But then why some of them are spirals, like disks, two-dimensional disks with essential rotational momentum, while others, so-called elliptical galaxies, absolutely have no rotation at all, no rotational momentum, but still they are made of the same stars. So the Henon-Hayley system was one of the examples when trying to analyze the dynamics of the stars in these disks. The numerical analysis, again, the computers were just arising in early 60s, and one of the computer methods provided, we can say, experimental observation, experimental proof of chaos going on in the spiral galaxies. And then later, in late 80s and early 90s, the problem of the stability of the solar system was reconsidered in an essential way. This problem, again, goes back up to Laplace and Lagrange in late 18th century, when they formulated the problem whether the solar system is stable or not. So it will remain as it is forever, or it will dissolve somehow or so. And they looked by their methods, so-called expansion over the smaller parameter, so study of a series of large number large number of terms, and to see whether there are so-called secular terms which are proportional to the time. And they saw that in first order of the eccentricity, which is very small, there are no secular terms. And then in some 20 years, Fourier and then Poisson, and then later in Darboux, they calculated the second and the second order terms. And again, they saw that there are no such terms. But such terms appeared in the third order. And just to illustrate how it looks and how they worked at that time, I will mention that one of the papers, one of the authors working at that time was Delaunay, who a paper published in French Academy of Sciences, Proceedings of the Sciences, the one formula in that paper takes more than 150 pages, one single formula, because formula contains so many nonlinear terms. How to deal with so many terms in the formula? And Poincaré, as I mentioned in later 19th century, found the ways how to deal with this so-called small denominator problem, and therefore his four-volume fundamental monograph was just called New Methods in the Celestial Mechanics. And so, since then, there was no breakthrough. And suddenly, in late 80s and early 90s, by Jacques Lascar in Paris. By the way, Jacques worked in the same Bureau de Longitude, the same institution where worked Laplace. They used the technique of Kolmogorov and created a software, the algorithm for the numerical study of this problem. And they succeeded to integrate onwards and backwards the orbits of the planets. And they came to the surprising conclusion that inner planets, namely compared with the Earth, so Mercury and Venus, have to undergo chaotic fluctuations by the large planets. And as a result of these fluctuations, within 3 billion years in future, the orbits of Venus and Mercury will intersect with fatal conclusions for the Mercury, because the mass of the Mercury is smaller than of the Venus. As a result, probable result, Mercury has to leave the solar system within 3 giga-years. Of course, it cannot be predicted precise date or time like we can predict the eclipses 100 years in future or before, or several, even 1,000 years. But because it is a chaotic effect. But it is it has to take place. So this is one of the conclusions. And the second conclusion, that the obliquity, namely the angle of the rotational axis with respect to the plane of the ecliptics of the planets, this obliquity has to dance, has to vary, fluctuate within essential interval. As you can see here, in the case of Mars, it is up to 60 degrees. And for the case of Earth, the situation is very different. Because of the presence of the Moon, these fluctuations are damped. They are very small. They are no more than around 1 degree. And can you imagine what can happen with the life, could happen with the life on the Earth, if the fluctuations of the axis of the rotation with respect to the ecliptic were up to 60 degrees? You can imagine it can be absolutely fatal for the life of on the Earth. And from this point of view, one can say that the Moon is a stabilizer of the climate on the Earth, and in certain sense on the life evolution of the life on the Earth. And while on Mars there is no such a stabilizer, and we know at least that up to now there is no atmosphere, there is no life, at least on the surface level, on some level, and so Mars possibly this effect which is there could have some role what has happened there. So I am mentioning these examples to show that how crucially these properties, chaotic and regularity, interface between them can in crucial way change the understanding which were used to, even for some problems which are 200 years old. Now, the dynamics of the clusters and galaxies, I already briefly mentioned. They are governed by Newtonian gravity. But still, the methods developed by Kolmogorov and later on unable to show that particularly star clusters like the one shown here, they are non-rotating spherical configurations. They are exponentially unstable. So, namely, small perturbation is growing increasing by exponential law, and the system is losing the initial conditions. Cannot memorize the initial conditions in very quick way. And now let me move to the early universe. As you know, and also mentioned during this meeting, during the last 20 years, we had essential breakthrough in the cosmology because of the measurement of the so-called cosmic microwave background radiation. The map is shown below, and to the right, to the left is the satellite, which provides the map. To the right is the so-called Wilkinson microwave anisotropy probe. Now, currently, it has just released the 9-year data of the measurements of this radiation, and you can see below is the map, which is in the color some scale or temperature scale, which are represented in some color bars. You can see in the center is the red one is the galactic disk, so the disk of our galaxy, while the rest is the cosmological signal, and this is the radiation which is arriving to us from 13 billion light years distance. Namely, it was emitted over 13 billion years ago. And
so 5 minutes more, please. 5 minutes more, please.
Thank you. And here I will say that this radiation is being detected by your TV sets at your houses because around up to 10% of the noise detected by the TVs to this radiation which is coming from the early phases of the universe. And here the study of the properties, which is called Kolmogorov stochasticity property, which is the level of the randomness in the signal. The signal contains both regular information, a regular component, and chaotic. It is well known. It is Gaussian mainly. This can be, one can calculate this 3D picture of the distribution of the randomness over the sky. You can see the red one in the center. This is the galactic disk. So it shows that it is a different signal of a different nature, while the rest, up and down, the hemispheres, are the cosmological signal. And of course, they contain a lot of information about the early phases of the universe. Let me move to the work we did with Roger Penrose on his conformal cyclic cosmology. Namely, we studied the properties of the maps here to the right with respect predictions of the conformal cyclic cosmology. And you can see, so there are the data of this WMAP satellite, which I mentioned before, some properties which are being predicted by the CCC cosmology. So the behavior of the structure which we're looking, you can see here, and it was just released again, I mentioned before, some week before. And you can see there are the 2D and then 3D structures which are fulfill some of the key predictions of the CCC cosmology. Let me briefly mention another application of these techniques. It's so-called Kolmogorov complexity. Kolmogorov introduced this in '65. Almost parallel, it was introduced in the United States by Gregory Chaitin. Namely, it is the it is called algorithmic way of representation of the information. The string, the minimal string which of the program which is needed to recover any system. Of course, I will not go ahead to the details, but just carry this message that it is a quite algorithmic, or let's say based, of course, on the concept of the Turing machine. Therefore, it is model independent. It is quite objective way of the squeezing of the information. So this technique can be used, and what I did some years ago, to calculate the Kolmogorov complexity of the human genome. Because in 2003 and 2004, the great program of human genomics released the human genome structure, and it was striking that one can calculate it, and it appears quite a small number, 10 to the 11th, which is quite a small number. And from here, I argued that in principle all the information which is on the human genome, and which is the major part of the other genomes, particularly for the mouse and the rat, were known also, and up to the others, which are common in the over than 90%. Then the squeezed, I'm finishing, the information can be packed and sent in a way to travel to the universe, and somehow supporting the concept of so-called panspermia. So let me conclude that the chaos and the regularity are together the inevitable properties of the universe. Thank you very much.
This is open for discussion or comments or questions from the audience, please.
You mentioned that in order to get a cosmological arrow of time, you have to start with decoherent initial conditions. Is there any physical reason other than, apparently we have decoherence or we wouldn't see a classical world, but is there a physical reason that you can define in the early universe for why we should have decoherent initial conditions?
In fact, we have not only this conclusion needs some reason, but also inflationary universe scenario, which is now one of the mainstream concept of the creation of the universe, is based on the chaotic initial conditions. So therefore, they produce Gaussian structure of the CMB, and so. Therefore, the non-correlated initial conditions are, at the moment, is one of the accepted cornerstones of cosmological scenario, as we understand. Not only in this context, but, for example, I said in inflationary scenario as well.
Yeah.
Thank you. Perhaps you could just say, for those who are unfamiliar, that you work with Penrose on CCC. The idea is that the universe, the Big Bang, were preceded by another universe, and Big Bang preceded by another, words, and that the universe, in some sense, is reincarnating.
Yes, of course, that work with Roger Penrose is essential from 2 points of view. One is conceptual, that the cosmology up to now is dealing with Big Bang, and what happens before Big Bang is considered outside of our discussions. This is the first, and the second, also I mentioned as a comment to one of the talks, that it is based on general relativity of Einstein, which is metric theory. Namely, the scales are crucial in general relativity and, of course, relativistic cosmology. While here, first, the conclusion that Big Bangs happen to be also before and can happen in future is changing all the conceptual background of the modern cosmology. And methodically, this is changing also the metrical approach of the Einsteinian general relativity, because this deals with conform mathematics, conform structures, namely when not the scales, but the angles are crucial. Once it is taken, and of course the empirical fact of the second law and the increase of the entropy, then the construction of the CCC, cyclic conformal cosmology, is coming up. Therefore, yes, thanks, Stuart, for this question. I wanted to stress that this is, of course, heuristically different from the cosmology which we deal, relativistic cosmology which we deal up to now.
Last question.
Thank you for an interesting talk. This question is from the perspective of psychology. And I noticed you mentioned that as one of the elements involving the arrow of time. One of the things that we struggle with is to come up with a dynamical picture of cognitive phenomena. And in your talk you said that of those ones you listed, they could all be included in one or two dynamics that you present. So what would you suggest as the dynamics for cognitive phenomena? Please help us.
Well, of course, it is not quite straightforward to describe, to give a precise mechanism, but the understanding of, is the following, that all these five, including psychological, can be reduced to the thermodynamical, including quantum mechanicals. They can be reduced to the thermodynamical. And with the link with each others, they can come up to the observable behaviors of the organized or complex systems. And one of those appearances could be some typological or so. But the structures are multi-structure systems, which are, I think, will be the subject of the next three talks here. And their interference with the quantum mechanics also is the link to the question you are saying.